Right. Well, last time it was Mid-Autumn Festival. 上次是中秋节. So happy Mid-Autumn Festival. 中秋快乐. Um, all the right things will happen, and if it doesn't happen, it was not meant to happen. 一切会是最好的安排. 没有发生的一切本来就不该发生. Enough said. 讲的够多，咱们继续做数学. So let's do some math. 嗯，关于导数，你只需要知道几个概念，就是关于 n 维导数。n 维 So regarding n-dimensional derivatives, you just need to get clear a few concepts. 有梯度，有 Jacobian，还有 Hessian。So there's the gradient, there's the Jacobian, and there's the Hessian. All right. 我们记得上次讲过，梯度就是梯度 f，等于向量 f 对于 x1的偏导数，f 对于 x2的偏导数，等等等，直到 f 对于 xn 的偏导数。要是 f 是有 n 为 x 向量的输入。So last time we know that the gradient is grad f equals vector partial f partial x1 partial f partial x2 dot 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 all the way to partial f partial xn if f is a function of n-dimensional vector x. Now, this is where the best Chinese textbook and the best, in my opinion, American textbook differ. 然后这里我们就开始有中国的最好的数学分析课本，还有美国的最好的多维微积分课本，有不同的定义了。According to Yeah, according to the Chinese textbook, the Jacobian is the gradient. Um, and yeah, this is the like n-dimensional f of n-dimensional x, or I mean m-dimensional f of n-dimensional x. So 据这个数学分析教程下册，长庚者史继怀编，Jacobian 就是梯度，嗯，数学分析教程下册，呃呃，长庚者者继怀。编，嗯，那么要是有 m 维的 f，有 n 维的输入，那么他们定义 Jacobian 就是梯度 f，就是呃偏好，就是 f1的偏好，的偏导，然后 f2这个偏导，一直到 fm 的各个偏导。写成矩阵。All right, so according to the Chinese leading textbook, the Jacobian is defined thus. In particular, it's the same thing as gradient of f. Um, the American textbook, 美国的课本, well, 在美国的微积分三，我们都学到了那个 Jacobian 是做积分的一个概念。So in American uh, multivariable calculus, we all learned that the Jacobian is something that's used for integrals. So this is Essential Calculus by James Stewart, second edition. Um, I think we need to learn implicit differentiation. 觉得我们不需要学引函数定义、定理。Jacobian 在哪儿呢？啊哈，thought I bookmarked it，我以为我把它书签了啊，在这儿自己听。Here we go. Okay. So we learned that the Jacobian is actually the determinant of the gradient matrix. 所以举他们来说，Jacobian 是它的 determinant，我记得在这里中文名字就是trying to find the Chinese name for determinant，叫什么列式还是什么？黄列式吧？Yeah. All right. 嗯，Okay, let's do it this way. Right, so this is the matrix, and then this is the determinant of the matrix. 所以这是矩阵，然后这是矩阵的行列式。 And then finally, the Hessian. 最后还有一个叫 Hessian. It's another form of the n-dimensional derivative or m-dimensional. 也是一种 n 维或者 m 维导数。I don't think that there is a Hessian in the American textbook. 我觉得，美国课本没有 Hessian. Just look at the index if you can't find it. 美国课本后面有一种目录，要是你找不到，有 Jacobian，有 Hessian 吗？There's a Jacobian. I don't know if there's a Hessian. No Hessian. Okay, look at the Jacobian. 没有 Hessian，但可以看一看那个 Jacobian。Yeah, yeah，他们只是在那个积分的时候才讲这个矩阵。So this is integrals，这是我们学积分的时候会见到的。Okay. But I know that in both the American and Chinese mathematical uh, general community, so I've seen it both in this book and also in the textbook at MIT, in specifically the class 18022 multivariable calculus. Come on, how come I can't copy paste? Jeez, do I have to write it again? 数学分析教程下册 and also 所以数学就是这个yeah 整个数学社区就是包括中国的什么数学分析教程，也包括麻省理工的呃一门课，我上过18.022，那就是多维微积分。 呃，他们都定义 Hessian 也是类似的矩阵。OK，像这样。嗯，对称方阵。它是用来做二阶导数的，used for taking second order derivatives。但它是一个 n 阶对称方阵，but it's a n by n square matrix, symmetric and square matrix。Okay, but to understand how all of these work and what is the difference between all of these, all right, this is really just a, partial derivative, but more general for, n dimensions. 但你想了解这一切和它们之间的关系和它们之间的区别，嗯，比如这个就是偏导数，但它是更广阔的偏导数，就是扩展到 n 维，然后，yeah，其实这个，and actually this one is I think this is different from what MIT taught. I think that MIT agreed with this one. Actually, I forgot what the MIT textbook defined says. I think, yeah, yeah. I think I think the Hessian, according to MIT, was the gradient according, or the Jacobian according to China. Okay. But all you have to understand is what is a differential. 但你只需要了解一个概念，叫微分。嗯，which is that the change in f，也就是说 f 的变化，这个是个 delta，OK？delta 跟nabla 是不一样的，so delta is different from nabla. Um, it's equal to the gradient of f dot dx1 dx2 all the way to dxn. And actually, if you want to take the OK，所以它就是梯度 f 然后叫什么那个点乘法向量乘法跟这个向量，也是有的人叫 Jacobian，有的人叫 Hessian，但反正就是这个，m 矩阵乘上dx1 dx2 xn. And this is where you can take a look at a free textbook that I gave you earlier that I wrote. 这里你可以看一看，我之前给你的免费课本，就是我写的，It's right here. Anyone can view it. 就在这里，谁都可以看。think 我觉得是71页，I think it's page 70. No. Oh yeah, this is from the Chinese textbook. 这是那个中国课本告诉我们的，就是可微则连续，可微则所有的方向导数存在，但所有的方向导数存在不一定说明连续，但我们上次见到过，we saw Clairaut's theorem before，这是 Clairaut 定理，所有的方向微分，也就是偏微分，都是连续的话，那么它是这个函数是可微的。这里有一些例子，there's some examples here。OK，这个 df 等于 f 在从 x 稍微挪了一小点儿 h 的位置，减去 f 在原来 x 位置的值，那就是 f 的变化。然后要是这个跟这个的差别，是小 o h，小 o 的意思是这个，当 h趋于零， 那么 f 就可微，然后这个这一个就是 delta f，然后它就是 f 的微分。So f is differentiable if and only if over here we got delta f, all right? So delta f, whichever one, um, which is the difference between f of a position slightly off from x by h, and h is really small, minus f at the position, the original position x. All right, so basically it's the change in f, and the difference between the change in f versus the differential of f, right? The delta f, which is called the differential of f, is small o of h, and this is the definition of small o as h approaches 0. And then you can generalize this to delta of f, where f is m-dimensional. 然后你也可以把这个概括推广到向量 f，就是 f 是 m 维的时候，那么我们就用这个矩阵乘上 h，其中 h 就是这个this is h, all right. The delta x，那就是 h 就是 delta x。What the heck？OK，所以 f 可微当且仅当delta f 等于 j 乘上 h 加 small o h 当 h 趋于0，这里 j 乘上 h 就是 f 的微分，就是 delta f。So f is differentiable, and here there should be a vector. 这里应该有一个向量 f. If and only if delta f is equal to j times h, right? J, some people call it the Jacobian, some people call it the Hessian, plus small o of h as h approaches 0, and j times h is the differential of f. Why do we care about this? Well, 为什么我们关心这一些东西呢？因为你要是能够计算 delta f 的话，你可以做三项东西。为什么关心这些？There's three things that you can do. 我们可以做三样东西，用这些。一，我们可以做逼近。So first of all, we can do approximations. Second of all, so for example, the Taylor approximation. Second of all, we can 比如泰勒展示。Second of all, we can do Lagrange multipliers. 第二，我们可以做拉格朗日。乘数法。 And third of all, uh, we can do directional derivatives. 第三，我们可以做方向导数。I think that I'll have to leave that for another class. 我觉得这个我得以后再多讲。But one thing that you do need to be careful of, 但有一个事情你得注意。So you can think about this. We know that df, 我们知道，就是你可以想一想这个，我们知道 df dx 等于dx df 分之一。So we know that df dx is 1 over dx df. But think about this. Does partial f partial x equal 1 over partial x partial f? 想一想，这个 f 对 x 的偏导数是否等于一除以 x 对于 f 的偏导数？ Well, I'll just tell you. 我直接告诉你们，df 等于这里的 df, 这里的 df. So the df here is equal to partial f partial x dx plus partial f. So it's just like, yeah, partial f partial x1 dx1 plus partial f partial x2 dx2. All right, all the way to partial f partial xn dxn. 它等于 f 对 x1的偏导数乘上 dx1 加 f 对 x2的偏导数乘上 dx2 加一直到f 对 xn 的偏导数乘上 dxn。然后df dx 用链式定理 so according to the chain rule df dx I forgot how to do that 链式法则 is equal to partial f, okay, df dx1, how about is equal to partial f partial x1 dx1 over dx1 is 1, all right, plus partial f partial x2 dx2 dx1 all the way up to partial f partial xn times dxn dx1. So clearly 1 over df dx1 well, So clearly partial f partial x1 is just part of df dx1. All right, so taking 1 over df dx1 is not quite the same as taking 1 over partial f partial x1. 所以显然这个 f 对 x1的偏导数只是 f 对 x1的导数的一部分。所以显然你要是做一除以df dx1，这个跟一除以 partial f partial x1，或者就是 f 对 x1的偏导是不一回事儿。嗯，其中呃一除以 partial f partial x1。In particular, 1 over partial f partial x1 uh compared to partial x1 partial f 然后相比 x1对于 f 的偏导数是不一样的。They're not the same. Okay, that's all for today. 今天就讲到这里。